Okay, start the lecture. Okay, so we'll move on to observer design today. Okay, and there are two different kind of observer design. One is called full order observer, and the other is a reduced order observer. Right? If you have a taking modern control, and you'll see there's much of a similarity here. Okay, so first of all, we still consider our state space equation. Okay. Now, in previous lecture, we learned pole placement control, right? So in pole placement control, the idea is you design your U, okay, and which is a negative k multiplied by x of k. So this is a negative feedback. K is a gain matrix multiplied by the state variable here, right? That's pole placement. So you have the feedback here, then you put it back to your system, and your system becomes g minus hk and x of k. Okay, so giving a proper value for the gain matrix k, you can place the eigenvalue of this matrix G minus HK at the desired location, right? Yeah. Now the only problem here is, you see the way of this pole placement is designed is negative K multiplied by X of K. Basically, you're multiplying by all the state variables. Or the assumption is, you assume that you know all of the state variable values at here. You have the information of the state variables, right? Yeah. But in reality, you may not have all the information. So let's say, for example, if x of k equal to, let's say, theta and theta dot, okay? Yeah. So theta is the position, theta dot is the velocity. So maybe you have a sensor for theta, but you don't have the sensor for theta dot, right? So basically, for the state variable here, you only have access to only theta here. You don't know what the theta dot is actually, right? It's a mathematical quantity, but you just don't know what the theta dot is, okay? So in this particular case, then you can't design your pole placement anymore, because your negative k is multiplied by this one here. If you don't have the information of this, how would you design your pole placement, right? Yeah. So in this particular case, you need this observer at here. Okay, you need the observer. So the observer idea is this. Here's your system. Here's the input to the system. Okay, and this is the output of the system. Okay, yeah. And in our particular case, our output here, okay, is y, okay, like this. So what we need is, we need a block here, we call that observer. Okay, we need the observer here. And the observer, what the observer would do is, it try to make use available information. What's available? Y is available here. Y is output. For example, in this particular case, okay, in this particular case, y of k equal to cx of k. If x is theta, theta dot, then maybe c is just 1, 0. Basically, y, the output of y is what? It's just a theta, right? Just a theta. So output is the position. So you have the position information. Input, you also know that, right? You also know the input. Then observer, okay, the idea is the observer will spit out an estimated x of k, okay, estimated x of k, based on the known quantity x and y. So in the later lecture, if we got time, probably the last lecture or two, we're going to learn a so-called system identification. That's a similar idea. System identification, you have input outputs. There's a system identification block at here. I try to space out the system parameter here. Okay. So now this observer function is to space out this x, not this guy here. Okay. It doesn't space out this. This x hat of k is an estimate of the actual x of k. Okay. So x hat of k is an estimate, okay, of x of k. And x of k is the actual number or actual values. So then, if I wanted to design a pole placement, I can simply grab this x hat of k at here and multiply by this negative k and then give it back over here. Okay? So that's the idea of this observer. A properly designed observer, okay, will actually have many advantages. For starters, you can save yourself a sensor, right, to measure the actual velocity. Okay, yeah. Now, of course, the whole question is, under what condition that we can design such kind of an observer, and how do we design this observer properly to give a proper estimate x hat of k? Because your u feedback pole placement, the negative k multiplied by this, your system design is purely based on the accuracy of the estimation of this x hat of k for the x of k. If the estimation is not good, then you won't have a good control, right? So you need to have a good estimation. So this is the overall picture here. If I break down the picture using our system here, right? So this is the state space equation system here, okay? And this is the observer we're talking about here. Okay, yeah. So first of all, okay, for the theorem is under what condition that we can design such a kind of observer. But before we move on, let me just write down simply the objective here. Okay. Okay. The objective is, okay, to obtain, okay, an estimate or prediction. Sometimes you can do of x here k plus 1, and based on the past information yk minus 1, okay, 1 up to maybe k minus n plus 1 here, okay, and u of k minus n plus 1. Okay, so basically there are n number here and an n number over here. Okay, yeah. So why is it called the prediction? Because this is a k plus 1, because actually the first observer design says a prediction type of observer. This is the information at the k plus 1, and these are information based on the k and the previous values, right? Previous values. So what we're doing is, if right now is moment is n, you're predicting the number 3 moment or step 3 values, okay, or estimating that value. The theory is, okay, if your system is completely observable, then you can design and observe, and you can have this state observation at here, okay, successfully you can design it. So basically the necessary and the sufficient condition for state observer, okay, or the design of a state observer is basically completely state, okay, observable. Okay, yeah. So completely state observable. In the lecture we learned, right? How do we check the observability? We check the observability based on G and C, okay, right? There's matrix G and C. Completely state observability, okay, is the necessary okay, and sufficient condition. Okay, yeah. And there are basically two different kind of observer. One is called a full order observer, and the other is called reduced order. So for full order, which is what we're going to talk about today, okay, full order observer basically, I don't care which one of the state is measurable or which one of the state is not measurable. So for example here, right, the x1 of k is measurable, but the x2 of k, you don't have a sensor for it. But when you design a full order observer, it's going to try to observe, doesn't matter which one is measurable, non-measurable, it's going to basically estimate all of them. Okay, it's going to estimate all of them. And for reduced order, right, as we learn next lecture, it's going to differentiate it here. Okay, so since this is a sensor for the theta already, and let's just only design an observer dedicated for this theta dot. Right, that's going to be the reduced one. Right? Yeah. So full order and reduced order. Okay. Yeah. Okay, so let's look at the full order observer in this lecture here. Okay, full order observer. We're designing, basically, remember, we're trying to estimate this x of k at here. Okay, estimate x of k. If you're trying to estimate x of k, you gotta basically come up with a model, right? Come up with a model, mathematical model for the estimation. Well, very simple model is, here's your system here, right? Here's the system matrix, here's system state space equation. So the initial simple model for this observer would be, okay, you don't do anything, just do this. Okay, just do this. Basically, you construct yourself, okay, a state space model based on the original matrix, system matrix G and H. And instead of calling x here, you just call x hat and x hat here. Okay, so that's a direct, basically sort of a personalization of this original system here. Then your y hat equal to c x hat, like this, right? Like this. So let's call this equation 1, equation 2 here. All right? Yeah. And your original system, right? Your original system is that x of k plus 1 equal to gx of k plus h u of k. Okay, let's call this 3 and here. Okay. So, what's the objective? The objective is to make this x hat, okay, the same as x of k, right? That's the objective. Then let's use 1 minus 3. Okay, let's use 1 minus 3 here. Right? Yeah. Let's use 1 minus 3. Okay. So then what do we get? If we use 1 minus 3, we get this guy, right, minus this one here. So x hat minus x equal to, so this minus this is gone, and g x hat minus x here. Right? So I got this. Now, if I simply look at this equation 1 and equation 3 here, they are basically the same kind of equation, just using different variables here, right? Just use different variables. So if you consider yourself, this is a differential equation number 1, differential equation number 2, but a different variable. So if equation 1 and equation 3 all have the same initial condition, then they're guaranteed that the equation 1 and equation 3 will change with the same thing, right? Will yield the same results if they have the same initial condition. Does that make sense? Right? But if the equation 1, equation 3 doesn't have the same initial condition, and that's basically going to be the problem here. Will the equation 1's result catch this equation 3? Okay, yeah. So that can be explained from this 1 minus 3 here. So if I call this as an error here, so basically we call this as an error, okay? The error of this estimation, this is the error of estimation, that equal to the G error K, like this, right? Like this. Okay. So now you can see now, error E represents the error between estimate and X. And now we have this equation here, which is what we call, basically we call that error dynamics. Okay, this error dynamics. What's the objective? Objective is to what we want is to make this E go to 0. So here's the error dynamics. Now tell me under what condition that the E will go to 0?
G is 0.
G is what?
G is 0.
Huh?
G is 0.
G is 0. Well, yeah, G is 0, that's right, but that's kind of too simple. What if G is not 0? G is what's G here?
It's a matrix.
What do we call this matrix?
State space equation.
That's right, that's the system matrix, right?
Yeah.
That's a system matrix. So what makes this G go to 0? So let's say if initially I have a E of 0 here, okay? If initially I have E of 0, so then what's E of 1? Is that right? If you keep going, what's E of 2? And keep going, then E of K is was that right? Yeah. And what do we want for the E of K? We want the E of K to go to 0. So what guarantee the E of K will go to 0? No, not initial condition. We're talking about the G at here. G is a matrix. So let's say if you don't consider G of a matrix, let's say this is a scalar here. This is a scalar quantity. This is some kind of constant at the beginning, right? There, I said when we have a different initial condition between 1 and 3, different initial condition. Basically, initially E of 0, it's not a 0, it's some kind of value. That makes sense, right?
Yeah.
So if this is a scalar quantity, not a vector, what value of the G will make this guy go to 0?
G has to be fraction.
Has to be fraction, has to be less than 1, or absolute value of G has to be less than 1, right? So now this is not a scalar, but this is a matrix. So which means, sorry, Mark? No, the determinant, the eigenvalue. The eigenvalue of the G has to be, the absolute value of that has to be less than 1, right? Has to be less than 1. Well, you learn pole placement. What does the K do? You want to place your K, you want to design your K such that what? The eigenvalue of G minus HK to be within where?
Circle.
Unit circle, right? To be within a unit circle. That's exactly what happens here. If the eigenvalue of this guy is within unit circle, you have this so-called what? The regulator, right? The regulator. This x of k will be regulated back to 0. Okay? So the same thing, right? The same thing here. Okay? The same thing here. So if I want it to be 0, then if the G eigenvalues, okay, are within unit circle. Basically, it's a stable matrix. Then E of k will go to 0 as k goes to infinite. Okay, as k goes to infinite. Okay. And as a matter of fact, maybe I can explain this a little better linear algebra way. So G is a system matrix. It's n by n. In one of the lecture, we learned similarity transformation, right? So what's a similarity transformation? You can get a matrix P, and then PGP will give you basically a diagonal elements and a diagonal matrix. The diagonal element is the eigenvalues, right? The eigenvalues. So this is what we call this matrix. G. Let's say W here, right? GW. Then the G matrix. If you do a little transformation here, the G matrix will equal to P and GW and P inverse, right? P inverse. Okay, yeah. Then linear algebra speaking, then G to the power of k, okay, G to the power of k will simply equal to P, G, K, and P inverse, okay, like this. So this G to the GW here, GW to the power of k, this is a diagonal matrix here. So that matrix is basically G, this lambda 1 to the k, lambda 2 to the k, and lambda n to the k. Right, like this. And then P inverse. So, of course, you see, what makes the whole thing go to 0? If lambda 1, lambda 2, lambda n is less than 1, and this matrix basically will go to 0, right? Yeah, so that's sort of a short proof. Okay, yeah. So then you look at this one here. So the only guarantee that to make this E of k goes to 0 is that the G's eigenvalue is within unit circle. And what does the G here? G represents the system matrices, right? The system matrix, which is basically the plant matrix, the zero-order whole equivalent of a plant. But would that be guaranteed that the G's eigenvalue will be less than 0? No, right? Your open loop or your plant, maybe it's unstable system. Okay. So in that particular case, then the observer, which is this observer here, it won't guarantee that it's going to have a good estimation of this x of k here, right? So that's basically saying is this simple design here only works when G has a stable eigenvalues. Okay, it won't work if G is not stable. Okay, so basically equation 1, okay, won't work. Okay, if G is not stable. Okay, or the open loop system, it's not stable. Okay, so in this case, then we have to rethink our design. Okay, rethink our design. To rethink our design is, okay, so let's modify. Okay, let's do a little modification. Okay, let's do a little modification here. So the modification is thinking is here. So we have the output here. So y equal to this. This is output. Output is measurable, right? Output is what the sensor. So you have the information here. You have this information, and we haven't made use of this information yet, right? Yeah. So what we want is, okay, so let's modify that observer. Previously, the observer is this. So this is the previous observer. Let's modify this guy here. Let's introduce a term at here, and this term is L y of k minus cx hat of k. Okay, it's this. So what does this term mean? So y is the measurable output. Cx hat is actually what? The estimated output. Right? So x hat is estimated states here. C by estimate states is the estimated output. The difference is the estimation error for the output. Okay. Then we multiply by a gain L at here. Okay. And this is actually like the pole placement. A gain multiplied by the feedback X. Right? But right now it's a gain multiplied by an error here, sort of error. Right? Okay. So let's modify with this one here. So the L here is called observer gains actually. Okay, it's called observer gain. If you look at the dimension of this L at here for a single input, single output system, so this is scalar here, right? This is scalar. And X is n by 1, so X hat is n by 1, so the L it needs to be an n by 1 vector here. Okay, n by 1. So let's see what happens if we introduce this L at here, right? If we introduce this L, okay, and how is that going to affect this whole design in here? So let's do this, and at the same time, your control. Okay, let's see if we're designing a pole placement. Okay. Your control is u of k equal to negative k x hat of k. Okay, x hat of k here. So then let's do a little manipulation at here. So look at this. Look at this one here. Okay, look at this one here. Expand this term. Okay, expand this term. So that's going to be what? L y minus L c x hat of k, right? X c x k. So you have x hat of k here. Oh, sorry, this is x hat. And you have a x hat of k at here. So this equation, okay, will become x hat k plus 1 that equal to g minus L c x hat of k. Right? So combine the two terms. Okay, combine the two terms. And the HU of k, so let's just keep it as it is. And plus Ly of k. Right? Ly of k. Okay? Yeah. So now this one here, right? This one here, in terms of the formality, in terms of how this looks like, if you wanted to compare, let's see if I wanted to compare with the pole placement after feedback, what does it look like? It's this guy equal to g minus hk x of k, then plus a 0 here, right? Plus a 0. And now for the observer, what it looks like is it's this equal to g minus lc x of k plus not a 0, maybe something here, but this is all known here, right? This is all known here. Okay? So in other words, if you look at this one here, this matrix at here basically will determine what? The dynamics of the response of this x hat of k, right? X hat of k. That makes sense? Yeah. So same question. Under what condition that this x hat of k will be basically affected? It will be affected by the value of this gain matrix L at here, right? The gain matrix L. Now, remember the objective. The objective is to make this x hat of k the same as x of k. Okay, so we do the same thing. Let's define the error as okay, x hat of k minus x of k. Okay, let's define this guy here. Okay, and we do the same thing as the previous step. Okay, as the previous step, then that means the ek plus 1 will be x hat k plus 1 minus x k plus 1. Okay, like this. Okay, yeah. So in this particular case, x hat of k plus 1 is this, and x of k plus 1, that's original system matrix, right? System equation. Okay. So let's use this equation. Let's call this is number 4. We're going to use number 4 minus which one? Minus number 3, right? Minus number 3. Okay. Yeah. So you know what? I'll slightly change the symbol here. Okay. Let me just, actually it doesn't matter, but just in case, let's define this is x minus x hat. So it actually doesn't matter. Okay. Okay. So basically we're going to use equation 3 minus equation number 4, right? Okay, equation number 4 here. And that basically gives us gx of k plus h u of k minus what? Minus this number 4 at here. Okay, minus this. So apparently you see I got this and this cancelled. Okay. And this gx of k minus that, minus y over here, okay, minus this. And what is the y of k here? Mathematically, the y of k is what? Cx of k, right? Cx of k. So this quantity here is actually just LC, right? X of k, okay? So you see there is gx of k, there's minus LCx of k. So that's basically g minus LC x of k. Then minus g minus LC x hat of k, right? Yeah. So take out this g minus LC at here. Then inside here is x of k minus x hat of k. X of k minus x hat of k is our error, right? So that basically give us g minus LC and e of k. So e of k plus 1 equal g minus LC e of k. See, right? Yeah. What does e represent? The error of the estimation. And what do we want? We want e to go to 0. What guarantee that the e can go to 0? The eigenvalue of the g minus LC needs to be within unit circle. And what guarantee that this g minus LC to be within unit circle? You have to choose the L properly, right? To make sure that the g minus LC has eigenvalues in the unit circle. Okay? It's like a feedback, it's like the pole placement. You got to choose your K properly to place the poles of the feedback system within unit circle at the desired location. Right? Yeah. So then what you need to do basically select L properly for desired observer pose. Okay, that's what happens here. Is that good? So the whole idea now becomes basically a similar issue as the pole placement now, right? As pole placement. Now, before we move on to how we calculate the K at the L, this is the diagram based on the modified observer. So there's no change for the system here. The only change this portion at here, right, is basically the equation given at here. Okay, equation given here. Okay? And ultimately it's the question of giving a proper gain matrix L. Okay, if you have a proper gain matrix L, your estimation here will catch this x of k at here. Okay, so that's the beauty of it. Okay, the mathematics. So this kind of a observer is actually what we call, it's sometimes we also call the Luenberg type of observer. Okay, yeah. Now the next thing is, how do we select L and how do we calculate the L, right? Okay, selection of the L matrix. Okay. Selection of the L matrix is actually not that difficult. It's actually pretty straightforward. We said we want what? We want this G minus LC, okay, the eigenvalue, okay, within a unit circle. Okay, at where? That's the location that you wanted to give it to the controller, right? That's basically you specify this L at here. So in other words, maybe what you want is you want this eigenvalue at the desired location. Maybe you want it at the P1 and P2. Okay, let's say for example it's a 2x2 system. Okay, yeah. Then basically you want z minus P1 and z minus P2 is your desired polynomial. Right? It's a desired polynomial. So you expand this thing here, you have your desired polynomial. Let's say you have a desired polynomial alpha z, right? Desired. Okay? And we want this desired one, basically what you want is you want this zi minus g minus lc, okay, to be the same as alpha desired. That makes sense? Right? To be the same as alpha desired. So that's the same idea as a pole placement. So give certain parameter for the L at here, calculate the parameters based on this alpha desired, right? And that's basically hand calculation. And for simple system 2x2, you can definitely go through this route, okay, to obtain the desired L matrix. And the other way is, as we learned, okay, when we learn pole placement, we learned one of the formula called what? Ackermann's formula. Okay, Ackermann formula. Okay, so let's see if we can make use that Ackermann's formula. Okay, yeah. So first of all, let's go just a little brush on this pole placement as to that Ackermann's formula. So if you recall, when we do pole placement, your basically your system is a gi minus g minus hk. Okay, if I go back to the top here, this g minus hk here, right? So that's your system matrix. We want the characteristics equation for this system based on this system matrix g minus hk. So that's basically what I write here. So zi minus this, that's going to be the desired, that's going to be the system polynomial. Okay, and we want this one, okay, to be the same as the desired one there, right? To be the same as desired. So this is zn my plus alpha 1z. Let's say this is our desired one. Okay, yeah. So if this is the desired, okay, and we call this as alpha cz, okay, alpha cz. Okay. Then the Ackermann formula for the pole placement is what? The k equal to 0, 0, 0, 1, and then h, gh, gn minus 1h, inverse alpha c g. This is Ackermann formula. Yeah.
Why is that you don't want the last term?
Here?
Yeah.
Yeah, it is. Sorry. Yeah. Okay. This is Ackermann formula, right? This is Ackermann formula. Okay. So now let's look at how do we make use of the Ackermann formula. So right now we can't make use of the Ackermann formula here because why? You look at this one here. There's a little difference though. See, this is a G minus LC. This is a G minus HK. So you look at this. If you do a little comparison here, what's known here? G and H, right? And K is the one we're looking for. But here, this what's known here? G and C. L is what we're looking for. So if this is G minus CL, in terms of formality, that'll be the same as this guy here, right? So that I can basically make use of it. But right now, this K here is behind H, but this L is before the C. So you cannot just say L equal to this, and replace the H with a C. So you can't do that, okay? Yeah. So we have to do a little a modification at here, okay? A little modification. But the idea is still we want our desired, okay? We want this desired. This is the desired one, okay? That equal to this G minus LC, okay? G minus LC, okay, equal to a certain desired polynomial. Okay, certain design. So this polynomial, I write it the same as alpha 1, alpha n. Then technically speaking, this is going to be different values from this guy here. Okay, yeah. Of course, you could make it the same, but this is another desired though. Okay, another desired. Okay. So all we do is this. Okay, yeah, and let's do this. Let's look at this guy here. Let's look at what's the G minus LC transpose. Okay, if I do a G minus LC transpose, and what would that be? This is what? G transpose minus LC transpose, right? And what is LC transpose? The property is C transpose L transpose. Okay, yeah. Okay, so now based on this guy here, if I look at this G transpose minus C transpose L transpose, and then if I compare to this guy here, this is G transpose minus C transpose L transpose. See, now they match each other, right? What match? This G transpose match that G. The C transpose match this H. And the L transpose is that K there. Make sense? Yeah. So then this G corresponding to the G transpose, and the H corresponding to this HC transpose, and the K there corresponding to this L transpose. Okay. So Ackermann formula. If Ackermann formula for the K is this guy, then which means Ackermann formula for the L transpose will be this guy here, right? Will be this guy. But what do we need to do? We have to change the H at here with what? C transpose. We change the G here with G transpose. Okay? Is that clear? Yeah. So then L equal 0, 0, 0, 1. H is replaced with C transpose. G is replaced with the G transpose, C transpose, up to how much? Up to where that the GT transpose to the power n minus 1 and C transpose inverse. Okay, inverse. Multiply by, this is your desired. This is the desire now, right? So alpha E. This is G, but it's going to be G transpose. Okay, G transpose. This is L transpose, right? L transpose. However, you don't want L transpose. What do you want? You want the L. So in the end, so you basically L equal to L transpose transpose. Okay? So L transpose of this whole chunk at here. Okay? Yeah. And that give you this one. So if basically consider this, right? This is one matrix, A, B, C. Okay, so we have three matrices here. Okay, three matrices. So when you have A, B, C transpose, that equal to C transpose, B transpose, A transpose. Okay? Yeah. So C transpose is transpose of this guy here. Okay? So it's alpha E. So transpose of this alpha E. Transpose of alpha E, what is alpha E? Alpha E is you replace the Z here with what? With the G transpose here, right? G transpose here. Then when you do another transpose at here, that transpose basically cancel each other, right? Yeah. So the beginning ones just become alpha E, G, like this. Okay, like this. And B, basically, B transpose the transpose of this chunk here. Okay, transpose this chunk. Okay, yeah. Now, inside this guy here, this is C transpose. When you have a G transpose, C transpose, this is actually what? CG transpose, right? CG transpose. And then when you have this guy here, that's actually, this is G transpose to the power of n minus 1. So you can rewrite that first as Gn minus 1 to the power of a transpose. Okay? Yeah, G to the power n minus 1 transpose. Same thing, okay? Same thing. Then multiply by C transpose. So altogether, that's actually Cgn minus 1 transpose. Okay? Yeah. So now each term, this is all bracket transpose, right? So then it's the transpose of this whole chunk. Transpose of this whole chunk is, if this is n by 1, it'll become 1 by n. Okay? And, basically you do the regular transpose. But this is the block matrix. Okay? Block matrix. So this guy become column first, and each one of the block here you transpose. Okay? So C transpose again becomes C. CG transpose becomes CG. And this guy here becomes CG n minus 1. And the inverse like this. Okay? Like this. And the end, this guy here, do the transpose. And of course, that's become just a column. Right? Just a column here. So that's your L. If you want to do CAN calculation using Ackermann formula, this is the formula. Okay? This is the formula here. Yeah. Okay? But if you want to use a MATLAB, okay, the MATLAB command is ACKER, right? ACKER. So when you use a MATLAB, let's say for the regular pole placement, so what you do is you plug G here, you plug H at here, and you plug this desired vector of P containing the desired pole location, and that's going to give you the K, right? It's going to give you the K. So this is a pole placement. Okay, pole placement. But right now, we're going to use this guy here. So actually, if I use this guy here, I'm basically trying to do this step here. Okay, trying to do this step. Doing this step here meaning actually what? You're using Ackermann formula. So it's not G, it's actually what? G transpose. So G prime. It's not H, it's actually C prime. Right? It's actually C prime. So P is still certain kind of a P. Okay? It's your desired location for the observer pose. What does the results here give you? The L transpose. Okay? Yeah, it's not L, it's the L transpose. So when you want to use L, you have to transpose this guy again. Okay? That's observability. That make sense? Yeah. So that's it. That's basically how you design an observer. Look at that. If you're interested, I have provided a similarity transformation, basically transforming the system matrix to observer format first, and then you can use that as a shortcut to do hand calculation for observer gains. But however, my requirement is you need to be able to use this equation here or that equation, no matter, for a simple 2x2 system, and you should do this hand calculation. Should be able, okay? Yeah, for observer design. Okay, so let's take a look at an example here. Okay. We're going to look at an example of the double integrator. We used the double integrator for poll placement in previous lecture. Okay, so double integrator. Double integrator is 1 over s squared. Okay. Then we learned that in previous lecture we can discretize this double integrator using zero-order whole equivalent, and that gives us a system which is this. As a matter of fact, that's the midterm. Was that midterm? Right, that's a midterm, right? Yeah. And yeah, by the way, the midterm is not that great. Yeah, I haven't started market yet, but when I was looking around, I don't think it's that good. Yeah. Frankly, I'm a little disappointed. So there are a couple of 100% though, and but there are some very miserable grades for sure. So I don't think it's difficult. You know, all the questions are basically from assignments, right? Very, very similar ones. Yeah. So you need to pay attention to the assignments, okay, and make sure you need to do it, and that's what's gonna be like in the final exam. Okay. So anyway, so let's look at this one here. So this is your G matrix, this is your H matrix. Okay, so let's say in this particular case, when we derive this one, we know that x1 of k represents a position, and x2 of k represents a velocity. Okay, so let's just suppose that I don't have the velocity information, I only have the position, but now I'm trying to design a full order, okay, observer for this system. Okay, for the system here, and we're going to design the full order observer. So let's just see what observer. Oh, I'm trying to design a deadbeat response observer. So design a deadbeat observer. Okay, deadbeat response. What does a deadbeat mean at here? That means where do you place the pole? Sure, yeah. Yeah, Mark. Pardon me?
As close to 0 as you can.
Not as close as actually right at the origin, right? So, which means your desired polynomial, it's just z squared, right? That's what the deadbeat means at here, okay? Deadbeat. So we want to place our desired observer here. And of course, let's say we're designing a pole placement. Then you have u equal to negative k x of k. Okay, in this case it'll be x hat, of course. Okay, so let's say I also want to design the k such that the pole placement, the poles of the closed loop, not the poles of the observer though. Okay, so the poles for the closed loop. What is the pole for the closed loop? It's the G minus what? HK, right? The G minus HK. That's the closed loop system matrix. So you want this guy here, okay, to have a location, let's say Z12 equal to 0.5 plus minus J 0.5, like this, okay? We did such kind of thing before, okay? So I want you to observe add here the requirement a little bit here, okay? So as you can see now, the observer pole location compared to the closed loop pole location, what will be the difference? This is basically at 0. This is not at 0. And as we learned, the system responds faster, or the response corresponding to the pole location, that when it's close to the origin, the corresponding impulse response is what? Faster, right? It's faster. So in this case here, the idea basically is, why are you placing this one as close to the origin? Basically, we're placing it at origin here. It's because we want our observer to respond much faster. Why does you want to respond much faster? Because your feedback k multiplied by the x hat, you want your x hat to catch this x of k as fast as possible. Okay, yeah. So a general rule of thumb is the rate of response for the observer should be at least 2 or 3 times higher, okay, than the closed loop pole location. Okay, yeah. It doesn't mean that you cannot place them at the same location, right? Yeah, but it's just for better system control performance, your observer gain, okay, or the pole observer pulse, okay, needs to be faster than the closed loop pulse. Okay, yeah. So once we have all of this thing here, and we actually just basically can use the Ackermann formula to calculate this observer gain matrix L. So we have the matrix CT, GT, CT, okay, this matrix here. So CT, GT, CT like this, right? Yeah. Or you can calculate using this one, doesn't matter. Okay. So that give you this 110T like this. Okay, I give you this. Okay. So at the same time, our L will basically alpha E, G, and then G inverse, okay, 0, 1, okay, like this. Okay, so alpha E in this case here just the G square, right? The G square, because the desired is Z square. Okay, and this one here, CG, that's the transpose of this whole chunk out here. Okay, and you can basically calculate. Okay, just plug it in there. And what would that be? And actually, yeah, it's going to be 110T, right? Yeah, inverse. Okay, so you do the calculation, plug it in, you get 2, 1 over T. That's your L. Okay, that's your L. Okay. If you're designing not a deadbeat observer, okay, not a deadbeat, then this alpha E, right, instead of Z square, it'll be having something behind it, right? Yeah, but it's the same idea. Okay, so here's what I did, okay, using MATLAB. I'll show you. Okay, so you should study this Simulink here, and you can easily modify that and implement on the system downstairs. Okay, yeah. So it's quite simple. Basically, we built the Simulink model, okay, based on this diagram that I showed you here. So basically, based on this diagram here, okay, it's the same structure essentially. All right, yeah. And of course, you need to make sure when you multiply the gains here, there are a couple of things here. This multiplication, right? There are different options. How do you do this multiplication? That has to be chosen properly. Okay. So for example, this is the gain matrix K here. So that's a pole placement, right? That's pole placement. That we have done that in the previous lecture. So what will be the proper gain here? Okay. And L, if you look at L at here, so this is a 2, this is 1 over T. That's what we just derived for the observer gain for a deadbeat response, right? Yeah. So in order to run this one here, you have to initialize in the workspace as what the T value and also the desired. I think in my case, I also had a desired pole location P1 and P2, so those has to be initialized in the workspace before you run it. All right? Yeah. But I'll show you a different way of using the Simulink in order to run this here. Okay? So one way to run this Simulink is you always initialize here. Say T equal to something, something. Like in this case, I choose T equal to 1 second, I guess. Yeah, maybe 1 second here. So basically, you got to initialize in the workspace. However, you can also do this way. Okay? So this is the you look at if you look in the Blackboard, there are 2 files. One is called version 1, the other is called version 2, and this is the version 2 at here. Okay, this is version 2. So in this case here, the initialization you can do this way. Go to View, go to Model Explorer. Okay. So here, if you have a 2 Simulink model open, choose the one which is this one that we're talking about here. Then there's a model workspace at here. Under the model workspace, there is a data source. Okay, there are different ones. I choose M code. Basically, I put my initialization code at here. Okay, so T is the sampling time. P1, P2 is the desired pole location for the closed loop. Okay, yeah. Actually, no, P1, P2 is not the desired pole location. This is a coefficient of the desired polynomial, okay, for the closed loop. Okay, yeah. So the benefit of doing this is, okay, the benefit of doing this is you don't need to initialize in the workspace. Once you open this Simulink file, the Simulink will initialize that for you. Okay, yeah. And also there's another benefit. Maybe not a benefit. It's the parameters that you see it here, those parameters here, it does not reside in the memory of the workspace. So you save yourself a little memory, basically. Yeah. However, the only catch up is if you want to know what a P1, P2, that you have to come here to access it, right? So if you look at the workspace here, you see those variables not here, right? Those not here. They're within that Simulink model space. Okay, model space. But I found it's very helpful because when you have lots of parameters to initialize, instead of just run an M file, you can just put it there. Next time, if you forgot, that's okay, right? You can still run it and everything's good. Okay. So if I run it here, okay, so let's take a look at the response. So the response basically taking a look at the output and the estimated value here, right? Estimated. So even though the output is measurable, we're just kind of comparing how is the observer compared to the actual measurement. So I believe the yellow one is the actual response, okay, and the pink one, okay, is the observer response. Okay, yeah. So eventually, basically catch up with the system here, right? Okay, yeah. So that's how you look at it. And the other thing is, I want to mention when you run this in here, where do you initialize initial condition? You initialize your initial condition by clicking on this here, the Z -1, right? Z -1 here. So basically, here is x of k plus 1. Here is what? X of k. Okay, x of k. So initialization should be done here. So I'm giving initial condition of 1 and 1 in here, right? Now the sampling time, this sampling time here, that needs to be the same as the sampling time that you used the capital T. Okay, yeah. So that otherwise you probably will have a problem here. Same thing for this Z here. So as you can see now, I'm setting my initial condition for the observer to be different from initial condition of this system, right? To the system. So that actually makes sense, because if you need an observer, you don't really know what the actual initial condition is, right, for the actual system. Yeah. But however, as you can see from the response, even it's just basically catch up with the actual ones, right? Yeah. That's observer design. It's the full order here. Okay. Yeah. So study this, and when you wanted to implement this pole placement plus observer on the downstairs there, as a matter of fact, you run your simulation first based on the model that I give it to you in the description file, and all you need to do is go to the experiment module, get rid of this chunk here. Okay, get rid of this chunk. Connect the wire, right, to the corresponding blocks. Remember the template, right? To the right terminal. That will be it. Okay? Yeah. So on the side of the project, so what you need to do is you need to do simulation first, okay, before you actually implement it. Okay, so simulation basically means you have that model of this setup, which is in my file on the blackboard. So implement your whatever you want to implement, whether PID or implement this guy here in the future, some other optimal control techniques. Okay, implement using Simulink or using the M file. Do the simulation first. But I think I would recommend using Simulink because it's a Simulink program down there, right? Then you go there and implement it. Okay, you don't do it if your simulation is not running well. Okay, yeah. As long as simulation is running good, you almost guarantee that the experiment will be okay. Okay, yeah. Okay, so that basically is the observer design. Now, in terms of observer, okay, I have another one called current observer. So just to complete this one here, I don't require undergrad note in the past to do any exercise using current observer, but I think I'll still got a little bit of time. I'll just touch upon it. It's not that bad. Okay, yeah. So what's the current observer? I think I changed the name current. Remember what I call this kind of observer here? Where's the observer? No, just a second. Where's the equation for the observer? Which is right here, right? Which is right here. Remember I had a name. I said this is x hat of k depends on what value? This, right? So k plus 1 depends on all the previous k's. So actually, we call this as a prediction type of observer. Okay, so you're predicting the next value, k plus 1. Okay, based on previous values. Previous means not including the current value. What is the current value? The current value will be y of k plus 1, right? So this is current. Okay, yeah. So the current observer essentially is to make use of this y of k plus 1 at here. Okay, yeah. So the idea is what you design is your observer, current observer is this. So you design yourself an observer like this here. Okay, so this is a z k plus 1. Okay, z k plus 1 this, and then x hat of k plus 1 equal to z k plus 1 plus l y of k plus 1 minus c z k plus 1. Okay, so this is the current observer. Okay, it's actually quite simple. It's 2 steps though. When we learn common filter, this is pretty much the similar kind of idea in the future, the common filter design here. So first step, k plus 1. Okay, it's a prediction. The second step, you're using the current output y of k plus 1 at here. Okay. of k plus 1. Okay. So idea is the same thing. And what about the error dynamics, right? What about this error dynamics? And how does that how does the expression, how would that give an expression for the error dynamics? And you can do the same thing. And if you define this, so that k plus 1 will be this. Okay, so basically x of k, x hat of k plus 1 is this guy here. X of k plus 1, and that's your original system, right? Original system. So original system equation minus this whole guy here, right? This. And where does that k plus 1 from? It's from here, so plug it here. Okay? Yeah. So if you do a manipulation, you'll get this guy here. So G minus LC G E. Okay, you get this. This is the error dynamics, okay, based on this current observer right here. Okay. So if you look at this error dynamics here, this is error dynamics. It's a different now, right? Previous is LC, but now this is LCG, right? It's LCG. Okay. So if we wanted to make sure the error goes back to 0, we have to make sure this G minus LCG's eigenvalue to be within unit circle. And we can use the same idea, right? So basically you can consider this is as one thing, right? As one thing. Then you can use this Ackermann formula again, right? Ackermann formula. So what's the Ackermann formula? That's basically the L at here is going to be the alpha E of G desired, okay? And then Cg at here, Cg squared, okay? And up to Cg to the power of n inverse. 0, 0, 0, 1. Okay, so that's the current observer right here. Okay, that's the current observer. Okay.
What is the benefit?
The benefit is basically you're making use of a little bit more information. Right? When you do prediction, you're only using the past information. So let's say I'm doing what will be the number 3, right? The results. You're using 2, 1, 0 previous information. But now we're using, okay, so I also know the current output here. So let's grab that value here, right? Yeah. So that's basically we can use a little bit more information. Will that give you better results? Maybe. Yeah. You know, statistically speaking, the more information you use, right, the better estimation would that be. Yeah. Okay. Okay? Yeah. So for undergraduate student, I have a homework. I'll upload that, and I don't need you to design a current observer like for graduate students. I said you can do, but you know it's not that difficult. If you wanted to use it, this one here, and that's fine. All right? Yeah. Okay, so I'll stop a little bit early here. Okay. So any questions? Good.